Okay, here we've got a ball on a wall. Let's have a go at drawing a picture of this. I'll get the wall on there first. And put a ball. And this ball is supposed to be tied by a string to the wall, such that if we kept going with that string, it would extend right to the center of the ball. There we go. So again, this is our wall. This blue distance is given as, I'm going to call it length L. That's the length of the string, and it's 0.32 centimeters. Here in green, we've got the radius of the ball, and that's given as 0.072 meters. And it was meters up here as well, actually given as 32 centimeters, which is 0.32 meters. Alright, that's our picture. We're supposed to find the tension in the string and the normal force exerted by the wall on the ball. Let's get a free body diagram of this situation. Here's the ball. Let's see, it's got a tension force acted on it directly away from the center. Weight force will be acted on it straight down toward the center of the earth, and the normal force be directed right toward the center. I'll call that N for normal, and there's nothing else touching it, so I got all the forces covered. This force is off at some angle. I actually want to find out what angle that is. It's angle theta right there, which looks like it's this one. In fact, if we continue this line up, drop a vertical, this would be theta, and then from opposite interior angles are equal. This guy is also theta, so it is at an angle theta where this is theta. I can get a triangle in there if I get another radius of the ball on the diagram. So let's do that. And get a right triangle on there. That's what I wanted to do. So this is also distance r. This distance, the entire distance there, from here all the way to here, is clearly just going to be, I'll call it d, and it's got to be L plus R, or 0.32 meters plus 0.072 meters, which is equal to, and I think I'd darken that up a little bit, 0.392 meters. So that's what D is. D is equal to 0.392 meters, and I need that value to get what this angle is. So yeah, I say R over D is going to be equal, that's opposite over hypotenuse, that'll be equal to the sine of theta. So R over D is equal to sine theta, or r is equal to d sine theta. Sorry, I'm looking for theta. Let's switch sides there. Sine of theta is just r over d. So theta is the arc sine of r over d. That is, theta is the arc sine of 0.072 meters divided by 0.392 meters. This value up here is what we found for d. Okay, let's go ahead and evaluate that. I'll take 0.072 divided by 0.392 equals, and then I want to take the arc sine of that, and I'm getting 10.5 degrees there, and go ahead and write that down. Theta is equal to 10.58. So 10.58 degrees. Alright, I'll need that. In order to break up this tension, I never labeled gave that force a name, but I want to call it the tension force capital T into components. So I need to break up T into components. Let's get a little vector component diagram going here. Call that the x direction, the y direction, then T got up at some angle theta, like that. That's my T. This will be Tx in magnitude. It's actually T in the minus x direction. Component in the minus x direction. I'll just call it the absolute value of T sub x. And then this is T sub y. Alright, need to break up T into components. I see Tx as being the opposite with respect to theta. So Tx magnitude is T times the sine of theta, and then Ty over T is the cosine of theta, so Ty is T cosine of theta. Alright, I think we're in position to draw another free body diagram, essentially copying that one down. I think I'll do this one in blue. Except I gotta replace the force T with its components. And it does Tx right through the center, so I can put the components on there as if they're acting at the center. Won't change the torque if you just slide a vector along its length. So I slide T along its length to the center there, and then I put the components on there. So there's Ty, Tx. Still got the normal force acted on there, and it's directed straight through the center, so I can put it and just slide it along its length. You can do that without changing any torques. And I got the weight vector W, which is equal to mg. And Tx we just found is equal to, I wanted that in magnitude, Tx, T sine of theta, and Ty is T cosine of theta. Alright. And there's no acceleration. I can write A is equal to 0, but that's true for any direction. And it is a statics problem. Let's see, if I sum the forces along the vertical, I'll just have one unknown, the mg and the T cosine of theta. If I went this way and have T sine of theta for the Tx and the normal force, both unknown. So I want to start with sum of the forces in the vertical direction is equal to 0 in this case. So I got Ty minus W is equal to 0, or t cosine of theta minus mg is equal to 0, so t is equal to mg over the cosine of theta, which is, did they give us the mass? We got, I guess, 0.24 kilograms, and this was 10.58. 0.24 kilograms times 9.80 newtons per kilogram, a gravitational force constant, all divided by the cosine. I think it was 10.58 degrees, but I do have to check. Cosine 10.58 degrees. Okay. So let's go ahead and evaluate that. I get 0.24 times 9.8 all divided by 10.58 degrees, and take the cosine of that, hit the equal sign, and I'm getting that that's equal to 2.39. 2.39. And the kilograms cancel. Once you take the cosine of that, you get a pure number, so it's just the newtons that are left. So T is equal to 2.39 newtons to 3 sig figs, and I think everything was given to 2 sig figs, so we should round that off, but I do want to keep that intermediate answer in case we need it. So T is equal to 2.4 newtons is one of my answers. Then the other question was, what's the normal force? So looking at that same free body diagram, we'll say sum of the forces to the right is equal to 0, and that's n is to the right, and then tx to the left. N minus t sub x is equal to 0, or n minus tx is t sine theta. So n is just t times the sine of theta, which is at 2.39 newtons that we just found, times sine of the 10.58 degrees that we found a while ago. Alright, let's plug those into the calculator. 2.39 times 10.58 sine equals 0.439, call it 0.44 to 2 sig figs, 0.44. And I'm going to write out the word newtons, since I'm using the symbol capital N for the normal force. And yeah, this is just newtons times a pure number. That's in degrees, but when you take the sine of it, you get a pure number. So you get both T and N. I think that's all they were asking for. Let's make a quick check on the question there. Find the tension in the string and the normal force exerted by the ball, or on the ball by the wall. I'm thinking I should specify direction. So I'll make this a vector and then give the direction as directly away from the wall. And then that's my answer. And over here, we want direction as well. The tension force, I'll call it away from ball. And along the string. If you had it to do over, I'd reverse the order and say it's along the string, away from the ball, but works fine the way I got it.